Welcome to example 6. In this example, we will classify a process vessel handling crude oil. Crude oil is a mixture of hydrocarbons that exists in the liquid state at ambient conditions. Of all the components in this assembly, the most likely source of release would be a flange connections or open-ended device that would result in a pool of crude oil collecting at grade level. We can use ExHAC to classify the area surrounding the vessel based on a pool release. Before starting the area classification, let's review some of the process parameters associated with the application. The vessel handles light crude oil operating at 800 kilopascals and 70 degrees Celsius. The vessel is incorporated into a manned facility that incorporates twice daily routine checks by operations. A crude release would be quickly identified, and it is estimated that the size of pool released would be less than 2 meters squared. The area is obstructed by the building, and this may compromise the level of ventilation in the area. We should also note that the vessel incorporates a PSV on top of the vessel. The classification of the area surrounding the PSV can be approached two ways. We can assess the classification using ExHAC, or we can apply a simplified method using guidance provided in APIRP 505. In this example, we will use a combination of methods and use API to classify the area surrounding the PSV. The PSV is likely to release crude vapors but only under abnormal process conditions that would likely result in a process shutdown. Let's begin our analysis. Let's create a new project. This is example 6. We will name this example crude vessel. Altitude is 500 meters. Minimum temperature is -40. Maximum ambient temperature is 40. The location is an oil battery. And we will mention in the project description that it is a crude process vessel. Next, we will configure our flammable mixture. This table displays the composition of the crude mixture and all the compounds involved. Note that we have listed only the compounds to C11+. ExHAC handles all heavy-end hydrocarbons as C11+, and it will estimate the vapor pressure of the mixture using C11 as basis. This will provide a conservative value for the vapor pressure of the mixture when we perform our analysis. Don't be too concerned if the vapor pressure does not match your own process data. So long as the ExHAC's vapor pressure number is higher than that of your process data, it will provide a conservative analysis. Next, we go to FM module. And since crude oil is not listed under a generic FM, we will create a new crude oil mixture compositions as shown. Click on FM and then on the Add New Flammable Mixture button. Define the mixture as crude oil. And then enter the mole percentages for our mixture. The mole percentages must add up to 100% before you can click the Save button. Our crude mixture will then appear in the Custom Flammable Mixtures section of the Flammable Mixture table. Next, we go to FM Analysis tab to create a new analysis for our mixture. Click on Add New FMA, select Crude Oil, and click Start Analysis. The properties of the flammable mixture will appear on the right, and the properties of its constituents are found when you scroll down. Given that our mixture is a hydrocarbon mixture, we can choose an alternative method of estimating the auto-ignition temperature of the mixture. Let's see what the AIT would be if we chose the mole weight average method for our calculation. Choose mole weight average from the drop-down menu and press Start Analysis. As you can see, there is no difference in the AIT value. Press Save Analysis and our mixture analysis will appear in the FM Analysis Management list. Now, we need to create the source of release. We will name this as our Process Vessel Pool Release. The pool release would likely result from a flange, valve or sample drain point on the vessel. Our stream temperature is 70 degrees Celsius. The stream pressure is 800 kilopascals. The grade of release will be secondary as we do not expect a release in normal operation. The ambient temperature is 30 degrees Celsius. Click Submit and the SOR will appear in the SOR list. Since the vessel is located outside, we don't need to create an enclosure. We can go directly to the HAC analysis. Select Create HAC. And then Example 6 for a crude vessel application as our project. Crude oil as our flammable material. A process vessel pool release as our source of release. And we will define our application as non-enclosed. Select Configure Analysis to begin our assessment. We expect a heavy gas release for the type of release. Let's review the wind speed for our assessment. Given that the vessel is partially obstructed by an adjacent building, we will select the value of 0.15 meters per second for an obstructed area. We will use the ExHAC default pool size of 2 meters squared. For the wind speed across the pool surface, the IEC standard recommends a 0.1 meter per second ventilation velocity across the pool. Let's input a 0.1 in the override cell. We will define the availability of ventilation as fair. All other parameters are not applicable. So let's start the analysis and review the results. ExHAC has estimated the vapor pressure of the release, at temperature, as 112 kilopascals. This will result in a mass and volume release rate, as defined here, resulting in a release characteristic of 0.156. This results in a medium degree of dilution. permitting a Zone 2 classification to be applied. ExHAC estimates the vertical extent of a release as being 1.7 meters, and horizontal extent of 3.6 meters, as indicated in Figure D.1. If we are satisfied with the results, we can save the analysis. Now, let's create a report and document our analysis. Go to the HAC tab and the HAC analysis list, and select our project. The HAC report is displayed for review. We can save the report and output an Excel spreadsheet result for inclusion in a larger report, if required. Before we move on, let's discuss how to classify the area surrounding the pressure safety valve. We can approach this two ways. We can use ExHAC to estimate the extent surrounding the PSV, using the guidance provided in Table B1 from the IEC standard. This, however, requires us to know the orifice section of the PSV. If we know this, we can run a new simulation in ExHAC, using a hole size of 0.1 times the orifice section, as suggested in the table. Another approach is to use simplified methods to classify the PSV. ExHAC provides a list of codes and standards that comply with the general principles of the IEC standard. API RP505 is listed as a suitable source of guidance, and incorporates a diagram that is directly applicable to our situation. Let's use this diagram in our assessment. Be sure to reference the API clause, indicated in the diagram, to ensure that you apply the diagram in an appropriate way. If we apply the results of our ExHAC analysis, and the guidance provided in API for PSVs, our diagram will look like this. A group classification of 2A, with an auto-ignition temperature of 204 degrees Celsius, corresponding to a temperature code of T3, would complete our classification design. Using the IEC tabular format to document our assessment, we can include the reference to API for the classification of our PSV, as shown. It only requires an additional line item to our Part 2 list of sources of release. We reference the API document, and the figure and diagram we based our classification design on, and our classification design is fully documented. Our classification design is complete. Our hazardous area classification design, for this process vessel application, is now complete.